So we're going to pick up where we left off, talking about a model that can account for limited growth. And so some of you may have heard of this before. It's a logistic model, and that's really just a fancy way of saying a limited growth model. Right? So a logistic model kind of works based on our starting presumptions, but it adds a little bit more. So if you remember from before, our basic presumption, our starting assumption, was that growth is always proportional to population size. And so the problem with that, of course, is that growth can't last forever. So what we need to do is come up with some way of limiting that growth, allowing it to grow proportional to population size up to a certain point, after which it kind of slows down. And so one way to think about this is if you have dp dt equal to k times p, then if the population is particularly small, right, it's going to behave this way. But if the population is big, like if the population gets really, really big, then we want dp dt to basically slow down and head towards 0, right? If the population is big. Now the problem, of course, you're going to run into is the words like big and small are not terribly descriptive. But remember that big and small, these are both relative to some upper limit or carrying capacity. Right? Some upper limit on the population. So if it's small relative to the carrying capacity, we want our model to behave just like derivative equals k times p. But if it's really big population, gets too close to that carrying capacity, we want our differential equation to slow down, or we want our growth to slow down and head towards 0. So we're going to add an assumption here. We're going to add the assumption that n is equal to some carrying capacity. And that means an upper population limit. Right? So that ecosystem, whatever it happens to be, has some upper limit for the population, and we're going to call that n. So what we're going to try to do is modify our existing model, right? We're going to start with our original model and our original assumption, and then we're going to kind of build on it. So that means that we got to add a little something to it. That means we want something like dp dt equals k times p times a little something. And of course, that something is completely and totally dependent upon what the size of the population happens to be. And so this something right here, we want it to, whenever p is much, much less than n, we want that something to be roughly 1. So if the population is really small, then this is just going to behave like dp dt equals k times p, because the something is essentially 1. And when the population is roughly equivalent to the carrying capacity, we want our model to make it so that the something behaves basically like 0, so that it's k times p times 0, or dp dt equals 0, right? This is going to halt our growth, but only when the population size is really, really close to n. So what I want you to do is hit pause on the video here in a second and see if you can come up with an example of some kind of expression, something that we could put inside the parentheses here that will behave like this, that will allow us to have a model that does this. So hit the pause and see if you can come up with a model that can do that. I'll wait. Okay, I told you I'd wait, but let's try something in for something. Specifically, we're going to try putting in 1 minus p over n. Now, take a second and convince yourself that this will work. This will do what we want it to do. And you can do that just by qualitatively sort of analyzing it. So K and P are our old friend, but this is a little something extra. So what happens if the population is much, much less than N? P is tiny compared to N. What does that mean? Well, you'd have K times P times 1 minus this thing right here. If P is dinky, dinky small, then this is a tiny little fraction. 1 minus a tiny little fraction is essentially 1. So in this case, dp dt is roughly equal to K times P. And if the population is equivalent to N, then what does that do for our dp dt? Well, if it's K times P times 1 minus the same thing on the top and bottom would be 1 minus 1. So we wind up with dp dt is roughly equal to 0. So it does exactly what we wanted it to do. But wait, there's more. Because we don't have to stop there. We can ask the question, well, what happens if the population is really big? It's even bigger than the carrying capacity. What happens if P is larger than N? What would that do to our dp dt? Qualitatively, it'd be K times P times 1 minus something that is a fraction that's top heavy, that's bigger on the top than it is on the bottom. And that means it'll be 1 minus something bigger than 1. And that means you'd have a negative in here times two things that we know are positive. So that means dp dt would be less than 0. And so this model predicts that if you have a population, a starting population, or a population at any point in time, that is larger than the carrying capacity, the model predicts that you will have decay. So we didn't even ask it to do this, but the model predicts decay if the population is larger than N. Which makes sense. If you drop off a ton of rabbits on a desert island where there's not enough food for all those rabbits, then yeah, they might survive for a little while, but they're going to start dying off pretty quickly. And you're going to expect a negative population growth, a negative population curve. So our model predicts something interesting. And now at the bottom, what we have, if we kind of analyze this, is called a logistic population model, or a logistic growth model. And the logistic model says that the rate of change of population is equal to some growth constant K times P. So it's still proportional to the population, but it also has this extra something, this 1 minus P over N. And so this is still our growth constant. K is still our growth constant. But we've added this extra little bit here, this N. N is our carrying capacity. And it's worth noting that you could rewrite this model. You could expand it and say, if you multiply that through, it would be K times P minus K times P squared over N. So notice, this is saying the rate of change of population is proportional to the population size, but it's also proportional to, in a negative way, the square of the population, right? So there's two terms in my population model. And if there's one thing we know about models with multiple terms, we know that every single one of the terms has to have the same units. And so that's what we're going to take a look at. We're going to do a quick, on the next page, we're going to do a quick unit analysis of our population model here, our logistic model. So if you remember, we have dp dt on this side, and we know that that has units of individuals over time. And we know from before that K has units of 1 over time, and that P has units of individuals. And so if this has units of individuals and K is still 1 over time, then multiplied together, they already give us the individuals over time that we know this whole side has to have. So what does that leave for everything that's inside here? What units does this have to have? Well, no big surprise, it winds up having no units at all. It is a unitless quantity. And the reason for that is P is individuals, N is individuals. And so you wind up with a cancellation of units here. And 1 is just 1, it's just a number. So this thing right here is a unitless factor that we've thrown into our equation. And it still works. But this unitless factor is just going to have the effect of allowing us to have limited growth. And so if there is an equation, a differential equation, we can ask the question, where do we expect equilibrium solutions? And if you remember, equilibrium solutions, this is just a fancy way of saying, what is P such that dP dt equals 0, right? So equilibrium solutions are just saying, where's the derivative equal to 0? Where is there no rate of change? And we can figure that out with a little bit of effort. All we have to do is set our dP dt equal to 0 and say that's going to be equal to K times P times 1 minus P over N. And of course, K is not 0 and N is not 0. Those are parameters that were set. So the question is, what's the P value? And there's one from this factor right here, and that's P equals 0. And then there's another from this factor inside here, and that happens to be wherever P is exactly the same value as N. So there's two places that we can expect equilibrium solutions, and they make perfect sense when you look at them. The first one is the same equilibrium solution we had before, which says you have no population, so there's no change. You can't have a change in the population if there's no population to begin with. The other one is a little bit more conceptual, but it makes sense given how we've defined things, is the population equals the carrying capacity. And that means you are at the equilibrium for your ecosystem. And so therefore, there's no change. So if you happen to be an organism or a population that is exactly at the carrying capacity, you would expect to have no change, no net change in the population, right? It may dip a little bit below and go up a little bit above, but it's going to stay right at that carrying capacity over time. So equilibrium solutions, no matter how complicated the differential equation get, really boil down to where's the derivative equal to 0? And specifically, it's what's going on with our dependent variable when the derivative equals 0. So this has a fancy name. This type of equation has a fancy name. It's called an autonomous differential equation. And autonomous, in this case, really just means that the right-hand side depends only on the dependent variable, not the independent variable. That's a fancy way of saying that our dP dt was a function of only P, right? The right-hand side is a dependent, or it depends only, it's a function of the dependent variable and not the independent variable, right? So this gets used in a lot of applications, and it turns out autonomous differential equations are much easier to solve. So what would other possible initial values for the population mean for growth and decay? So we're going to set up a little if-then table here. So we're going to say if the initial population is, and then over here, then we're going to say then we expect over here. And so we're going to set up this relationship between what's going on with the initial population and what do we expect. Well, we've already decided that if you happen to be exactly at the carrying capacity, then there's going to be no change. So if the population, the initial population is exactly the carrying capacity, then that leads to no change. equilibrium, right? So no change in the population. But what happens if your population is a little bit under that? Specifically, if your population, your initial population, starts off between 0 and the carrying capacity. If it's somewhere in that range, then we expect there to be growth. Because, of course, if P is slightly less than N, this thing in here is going to be a positive number. And so you'd expect growth. We expect growth in the population. But we don't expect it to grow forever. We expect growth in the population that levels off as P approaches N, right? As the population approaches that carrying capacity. And of course, there is this third possibility, and we hinted at it this last time. What happens if your population is larger than your carrying capacity? Well, in that case, your population is larger than the carrying capacity, this thing becomes negative, which leads us to a negative rate of change. We expect decay in the population, and that will level off as well. Level off as the population, P of T, I should say, approaches N, right? We expect our population to level off. And sure enough, when you look at the graph of one of these solution curves, we see exactly this behavior. We see behavior that if you look at P of T versus T, if you start off below some carrying capacity, and we'll call that P equals N, if you start below some carrying capacity, then your curve, using the kind of blue, it's going to grow really rapidly and then sort of level off like that, taper off as T goes on. If you start at the carrying capacity, then you wind up kind of hugging this dotted line forever, that you just don't go anywhere. And then, of course, if you start above the carrying capacity, you expect there to be some decay towards the carrying capacity. And sure enough, this is exactly what we see when we look at the graphs of solutions for our logistic curve, our logistic growth model, which we see at the top of the next page, which looks like this. These are curves that we've drawn for our logistic graph, our logistic growth curve, right? And so what we're seeing here, what we're looking at here, is three different circumstances. We're looking at the situation qualitatively where P, initial condition, is greater than the carrying capacity. These guys up here are greater than whatever this carrying capacity happens to be. We're seeing right on this dotted line exactly the initial population is equal to the carrying capacity, and then everything below, all of these initial conditions below here, are places where the initial population is less than the carrying capacity, but still greater than 0, because of course populations below the axis don't really make much sense for our situations. So we're seeing all these over here are different initial conditions. But look at what they lead to. Every single one of these initial conditions, all the curves eventually behave the same way. So I don't have to know what the solution to that logistic differential equation is to know that in time, all populations head towards the carrying capacity. Whether you started below, at, or above the carrying capacity, you're going to head there eventually. So down here in words, what does this graph tell us about the behavior? Well, it says that as t approaches infinity, the population is going to approach the carrying capacity value. And this, of course, is a limit argument, right? We're making a limit-based argument. The limit of, sorry, I can't talk and write. I'm talking right at the same time. But the limit of P of t as t approaches infinity is n. That's the argument that we're seeing here. So even without solving for P of t, and this is the important part here, even without solving, the differential equation. We know not what, but how the solution curves behave based on qualitative analysis. Oops, let me scoot this up. And this is pretty cool. You can say what happens to the general solution. In general, what happens to P of t for this particular, or for this differential equation. We know that the long-term behavior for my solution is going to be the limit as t approaches infinity of P of t is going to be n. And we know that based on the differential equation, just analyzing the differential equation. So that gets us to the end of this section. You'll notice there's still a couple of pages, but I'll talk about that in a second. Down at the bottom, I give you a little heads up that you're going to have to do some reading, specifically about the predator-prey model example that's on pages 12 and 13. You're going to want to do that before doing problem set 2. Problem set 2 is a ways in the future, depending on when you're listening and watching this video, but you're going to want to watch that or read that before you tackle problem set 2. You'll make sense of that. But I will also point out that there's 2 pages after this, and they are examples from the text, and they're practice problems. So you'll notice I'll say from section 1.1, I want you to try problem number 5 and problem number 10. And what I'm going to do is I'm actually going to write the solution, and then I'll post the solution for you to check out, right? Not as part of a video, but just as a PDF of the solution. I want you to try those problems, give them a go, and then I'll post the answers so you can see those and go from there. And that gets us to the end of section 1.1. Thanks for sticking in there.